And let's see. I'm going to be talking about hash functions, which we talked about a little bit the other day, but let's write it down a little bit more formally, what we care about. So today we're going to be talking about hash functions. For the record, this lecture and the next lecture are a combination of a bunch of different sources. So they're not entirely in your book. They're also not entirely in the PDF I linked, but it'll be some combination of things. The recommended reading I had in the online on the class website covers some of this material, but not all of it. Okay, so many of you have heard of hash functions. There are many different ways you can use them, but intuitively, the basic idea is it's sometimes helpful to sometimes randomly map numbers. Randomly map numbers. But what do we really mean by that? So like, if you want to, what we mean by that a little bit more formally is given a domain, let's call it U for universe, and a range, so an output range, let's call it M, so a set of integers from 0 to m-1. So what would be a truly random hash function? So a truly random hash function well, I mean, it's a map. It's a map from H from the universe to M, where each of H of X is an IID uniform random variable in M. Okay, so I'm abusing notation a little bit, but basically what we're saying is that H, you can also think of H as a, well, size of the universe, dimensional, random variable chosen uniformly at random from the set of functions from U to M, or in more set direct notation, you can think of it as this set. Now, what's the problem with using these truly random hash functions? Yes, they're very, very expensive. So how much space does it take to store one of these hash functions? So like if you want a particular map and you want to reuse that map again later, well, that means that for every single element of your universe, you need to store what it randomly maps to. And so this takes up the cardinality of U times log 2 M bits of space complexity. Because for every element in their universe, we need to store what we're randomly mapping it to. So basically, you're taking, for each element, you're taking an instantiation of a random variable and you're asking, well, what is the random number I'm going to always assign to this particular input? So this here is from each element in U, and this is store what it maps to in M. So this is pretty impractical. Because you're basically storing all of these, a bunch of random variables as big as your universe size. So now, what is a hash function in general? So a hash function H from U to M. One way of thinking about it is that it's a random variable in the class of all functions U to M, but not uniformly distributed. Not necessarily uniformly distributed. Necessarily uniformly distributed. Okay, so what we're meaning is there's a space, in order to choose a truly random hash function, you're basically choosing a truly randomly a uniform function from the space of all possible functions from U to M. But maybe like you only need to choose from some subset of that. Maybe you can say, well, I don't want to choose from all possible functions, but I only want to choose from some subset of them, and that'll approximate the statistical properties I care about in the sort of random way. So in practice, we care about both the speed and the space that we're using to store it, in addition to the statistical properties. What do we mean by space? Well, that means it's a random variable, but we want a particular instance of this random variable, right? And so in order to have the hash function map to the same thing each time, you have to store your hash function. If you want to store a truly random hash function, you need this u log m space, because you need to store where every single element maps to. But maybe you can just store a smaller amount of random information and have a random variable that's defined on the smaller with this more concentrated distribution that still gives you the same properties. So well, let's give a trivial example. So let's give a trivial example. Trivial. What's a trivial example based on this definition? So let me make it a little bit easier. Let me say I'm just going to have a smaller universe from M to M. What's a trivial example of a distribution over the set of functions from M to M? Yeah, just pick one thing. So from this definition, you could let this always be the identity function. So this is a random variable where all of your probability mass is on the identity function. It's not a particularly useful hash function, but you could argue that in some ways it is a hash function, at least by this definition. You have some distribution over the set of all functions, and you're putting some probability mass on one of them. Now, this is not so helpful, but another example, which is a lot more helpful actually, and which actually ends up with a lot of nice statistical properties. So one of the problems with the identity function is that it doesn't really map things randomly. And so there's some sense in which intuitively it's not doing what we want a hash function to do. But of course, we haven't really defined what we want the hash function to do, so it still fits into our definition so far. But let's take another example. So what if we have a prime number? So we're mapping from P to P for a prime P. And we're going to have this be given by h of x is equal to ax plus b mod P. Or you can think of this as just all operations in the finite field of order P, where A and B are uniformly randomly chosen in P. Okay, so now what we have here is we have a family of hash functions parameterized by A and B. And this is relatively fast to compute and you're only storing these two random numbers instead of storing the cardinality of u random numbers. Or instead of storing p random numbers or whatever. It turns out that this actually has a lot of the statistical properties that we care about. So let me give another definition. So a family of hash functions, and let's call this H. Let's say a family H of hash functions in script of hash functions. Little h from U to M is universal if for any x and y in U with x not equal to y, the probability over h drawn from this family. And so if our family was the set of all possible functions, that would be different than if our family was the set of all of these functions based off of this prime method. Okay, so that is the distribution. And the reason we have to do this is because we're going to make arguments that are based on probability, right? And so some of you have probably heard of hash functions from computer science like SHA-1 or MD5 or things like that. And these are cryptographic hash functions, but there's no randomness involved, right? And so what does it mean to say that to take an expectation over a hash value if everything is completely deterministic? And so in order for us to say anything about and prove anything about using these probabilities and expectations, we have to actually have some randomness in there. And so in our cases, when we're talking about hash functions, we're really talking about a family of hash functions and we're drawing one at random. And that's what we're taking all our expectations over. So probability of h from h of h of x is equal to h of y is less than or equal to 1 over m. So what property are we trying to approximate? So note, the probability is equal to 1 over m for truly random. Right, because if you had a truly random hash function, then each variable would be mapped randomly to one of your m things, and the chance that the two are equal will, once you set one of them, the chance that the other one's equal to the first one is just 1 over m. Okay, and so what we're saying is for a universal hash function, well, the collision probability is low. So that's one of the many properties. So if you're talking about this entire family of all possible hash functions from u to m, so this truly random hash function, it has a ton of statistical properties, right? Because you have so much randomness. Every single thing is IID distributed. Here, we're saying, well, we're not trying to get every single thing is IID distributed. We only want that the chance that they collide to be low. And this is important for a number of applications because you might want to, well, use your hash function to make sure that two different things don't collide in the hash table. So we'll talk a little bit about that in a moment. Or you might want some slightly different properties. So for example, maybe you actually want like 10 things to be uniformly random, but not necessarily all things to be uniformly random. And there are also ways of constructing that. And so that'll be something we'll get to, probably not today, probably on tomorrow, in terms of the independence of your hash functions. And in order to construct that, we'll actually be making use of some results from prime fields. And so there'll be some nice callbacks to algebra in these couple of days. Okay, any questions so far? So basically what we're saying is that family of hash functions is universal if the probability of hash collisions is low. And I'm going to define something, another concept, which is C approximately universal. So basically, for it to be universal, the chance that they collide has to be less than or equal to the chance with a truly random hash function. C approximately universal just means that the probability of h of x is equal to h of y is less than or equal to c over m, where c is some constant. Okay, so you're saying, well, the collision probability might be worse than a truly random hash function, but it's not too much worse. And if it's not too much worse, then often you can still prove the same things you want to about your algorithms. So let's give an example. So if u is less than or equal to m, question, is the identity function f of x equal x a universal hash function on u to m? So remember how I said that you could consider the identity function to be a hash function, but it doesn't have many of the nice statistical properties we care about. Does it have this particular nice statistical property? If the size of your universe is small, the size of your range. Yeah, so yeah, exactly. So I'm getting a couple nods, and also in chat. The probability of collision is 0 if you're just taking the identity function. And so clearly this is universal if the size of the space you're mapping to is bigger than the size of the space, or bigger than or equal to the size of the space you're starting with. What about if u is greater than or equal to m? Well, clearly then you can't just use the identity function, but let's say the mod function is the mod function f of x is equal to x mod m universal on u to m. What was that? You said it depends how much bigger. Let's say it's much bigger. Yeah, so the answer is no. And even if it's not that much bigger, it's going to pretty quickly not be universal, because in order for it to be universal, this has to be true for all x and y. So what if I choose the quantities 1 and 1 plus m? How often do these collide? Yeah, these collide with probability 1. And so maybe if you had some randomness in here, like maybe instead of just taking x mod m, maybe you took x mod some random number, then maybe with that randomness, this would become a something like a universal hash function. But certainly we don't have, the problem here is we don't have any randomness, and you can deterministically say these two things always collide, even if it's only slightly bigger. Okay. So I have another 8 minutes. I'm going to talk a little bit about a couple applications of this idea of universality, why we care about this particular statistical property, and we will be talking about other statistical properties we're trying to construct. So how many of you have heard of hash tables? Okay, a few nods here and there. So we're going to talk about application to hash tables. So this topic would be something you'd see in an intro CS data structures class. But we're going to examine it in the context of these sorts of hash functions, and then we're going to generalize hash functions to something slightly stronger. So application to hash tables with training. Okay, so this is the basic problem. Suppose we have a set S of length n of integers in the set U. Okay, so integers from 0 to U minus 1. So how long does it take to check if a particular integer is in there? Does it take to check if a particular integer x is in S? Well, the answer to this is that it depends on how you store S, on how we store S. And this is basically the motivation behind the study of data structures, is that how you store your data makes a really big difference in how quickly you can access it. So, well, let's start with the most naive possible thing. Let's say we're just storing it all in an unsorted list. How long does it take to find whether or not a particular integer is in your set? Yeah, O of n. You look through your entire set and you see if they're equal. This takes O of n time, call this time, and let's say, and you're also storing the entire list, so it takes O of n space. What if you have a sorted list? Well, that's a little bit better, right? Because then you can do binary search on it. You just say, oh, well, is it bigger or smaller than the middle element? And then you separate it out. And so then it takes O of log n. But it still takes O of n space via binary search. Okay, well, are there quicker ways of doing this without using hash functions? Can you do better? Well, what if I gave a bitmap instead? So what I do is I just have a really, really long bit vector because everything is an integer in U, right? So if I have a linked U bit vector, I just store 1 if that particular integer is there, I store 0 if it's not. Well, then it turns out that if I use a bitmap like that, it takes O of 1 time, because I just need to check if that particular integer is set to 1. But then this requires a lot more space, right? This requires O of U space. Because you're basically, instead of just storing your list of your set, you're basically storing a bit vector corresponding to your entire universe. And so this does work, but it takes up a lot more space. And this is where hash tables come into play. So hash table of size m greater than or equal to n, where we have an array of array L of m buckets. So what this looks like is, instead of a bitmap where you'd have all your different positions, so in the bitmap you have all your different positions up through U, and you're storing a 1 or a 0 in each of these, right? So instead of doing that, what we're going to store is, instead we're only going to have it to up to length m, and because that's what we're mapping our hash table to. And then in each of these places, we're storing a bucket of multiple items. So maybe 5, 7, and 91, maybe an 11 here, maybe 40 and 24 here. So we're storing all these buckets. And the way we're storing these buckets, we're going to call each of these L of m, because it's going to be a bucket in position m. And what we're going to say is that in each bucket, bucket I, we have an unordered set or unordered list of all items x in our x in S, such that h of x is equal to I. Okay, so we're going to use some hash function. I haven't defined what hash function yet, but some hash function that maps to some things between 1 and m, and then puts that item in there, wherever it maps to. Okay, and so now what happens if we have universality? So if h is universal, by which I mean the family of hash functions that h is drawn from. If h is universal, and our query x is not in S, well, then we can figure out how long of a bucket list we need to look through. So then we let I of x, let's say I of y be the indicator variable, for the event h of x is equal to h of y. Okay, so that indicator variable is going to be 1 when you have when y and x collide in the same bucket. Well, then we can compute the expected size of the list that we're going to have to look through. So then the expectation over hash functions in this universal hash set is going to be of the size of the bucket that we care about, which is going to be a bucket h of x, right? Because that's the thing we're checking. Is going to be the expectation over h of the sum of all these indicator variables, I of y, because we're asking if those particular items collide, and we can bring that by linear of the expectation. This is just the expectation over h of I of y, which is equal to the sum from y in S of the probability over h that h of y is equal to h of x, because it's an indicator variable, and so the probabilities work out that way. And so this turns out to be less than or equal to n over m, which, if you recall, because we had m is greater than or equal to n, this is less than or equal to 1. And so in expectation, we only need to check a list of size 1. So therefore, queries are average O of 1 time, and space is O of n as opposed to O of u. So what if h were only approximately universal? Say it was 2 approximately universal, what would happen? But c is a constant, and it's O of 1, and so it would still be O of 1 time. But yes, you're right. So this number here would be c instead. Or sorry, you'd have an extra c here instead. And so you still could set things up so that you had on average 1 thing, but your list would have to be bigger, or you'd have to allow for 2 collisions instead of just 1. And so that's basically why it turns out that for a hash function and for hash tables, you don't actually need a truly random hash function. And it's a good thing we don't need a truly random hash function, because those are too expensive to use anyway. So instead, you can get away with having something that isn't really truly random. Like you'll notice that even the identity function, if your set is small enough, satisfies this particular criteria. But there are ways of constructing these universal hash functions that are relatively cheap. We'll talk a little bit more about a couple of them next time. One of them will involve using prime order fields, basically. So this will be that connection. And we'll also talk about a couple other applications, as well as applications where universality, this condition, is not good enough. So if you want something to think about between now and tomorrow, you might think about how we were using hash functions with the probabilistic sketches, and think about whether or not a universal hash function is good enough for things like a log-log sketch. Hint, the answer is no, for reasons that will become obvious tomorrow. And I think I should end there because it's now 4:01. Thank you all very much.